Beneath the weightless digital mist of the cloud lies the heavy industrial reality of a windowless concrete fortress. Modern hyperscale data centers are sprawling industrial complexes. They cover dozens of acres of land, engineered to physically house millions of tightly packed servers. To keep those servers running, a single facility can draw hundreds of megawatts of continuous electrical power straight from the municipal grid. That is enough energy to sustain a mid-sized city. That incoming raw electricity is volatile and turbulent. But deep inside the facility, the microscopic transistors of a server rack require perfectly smooth, uninterrupted power to function. The internet survives inside heavy industrial environments that require rigorous mechanical and electrical engineering to keep the hardware from destroying itself. If power cuts to those racks for a fraction of a second, the consequences are immediate. Critical databases corrupt, structural data degrades, and enterprise companies lose millions in instant downtime. Relying directly on the city grid is impossible. Municipal power constantly suffers from microfluctuations, voltage sags, and spikes that would instantly fry sensitive networking equipment. This gap is managed by mission-critical facilities engineers. Their job is to design specialized electrical systems that intercept the raw city feed, scrub out the anomalies, and deliver a perfectly neutralized current to the data floor. These facilities function as active, heavily fortified citadels, locked in a continuous 24/7 battle against electrical instability to protect the hardware inside. The defense begins at the intake level. In these massive electrical utility rooms, raw high-voltage grid power first enters the building. If that grid feed drops, the facility immediately relies on its primary backup systems. Massive banks of uninterruptible power supply batteries instantly take the load, bridging the critical seconds until industrial-scale diesel generators spin up to take over. This outlines redundancy. An architecture is the minimum equipment capacity, like a single UPS, needed for the server load. Adding a backup creates N+1, rerouting power if the primary fails. 2N duplicates everything. Mirrored pathways eliminate any single point of failure. Downstream, automatic transfer switches and power distribution units instantly route this cleaned, redundant energy directly into the server racks without requiring any human intervention. Engineers achieve continuous uptime by mathematically layering overlapping pathways of failure recovery into every stage of the power chain. Once power is secured, the next immediate threat is heat. Millions of computing processes continuously generate extreme thermal exhaust. Extracting that heat requires heavy-duty cooling infrastructure. Facilities deploy specialized HVAC configurations, including computer room air conditioning and air handler systems, to aggressively push cold air through the aisles and pull boiling exhaust away. This creates an engineering paradox. Running these redundant cooling systems requires massive amounts of electricity, placing data centers in direct conflict with global sustainability mandates. This chart tracks power usage effectiveness, or PUE, the definitive metric engineers use to balance this conflict. PUE is calculated by dividing the total power entering the facility by the power actually consumed by the IT equipment, aiming for a target efficiency score of 1.0. Mastering this cooling infrastructure prevents imminent hardware meltdowns on the floor while dictating the environmental footprint of the digital economy. Overseeing these mechanical and electrical arteries is the facility's control room. Here, engineers monitor millions of telemetry points streaming from the power and cooling networks. Specialized SCADA and building management system networks tie everything together. This automation allows the building to detect micro-fluctuations, isolate faults, and self-correct anomalies far faster than human reflexes allow. Even fire protection requires precision. Standard sprinklers would destroy the servers, so data centers utilize advanced detection and suppression systems that flood the room with clean chemical agents to extinguish flames without leaving hardware-destroying residue. Operating inside these environments carries severe physical risks. Engineers perform routine maintenance near massive electrical loads, where a single mistake can trigger an arc flash, a lethal explosive release of high-voltage energy. While these fortresses are highly automated, rigorous human safety protocols and split-second engineering decisions remain the absolute last line of defense. The global demand for this physical infrastructure is expanding rapidly. We are in the middle of an immense construction boom for hyperscale, cloud, and edge computing facilities to support the next generation of digital traffic. Constructing and maintaining these buildings is currently bottlenecked by a critical global shortage of specialized MEP, IT, and facilities engineers who understand these interconnected systems. The Technovision Data Center Foundation certification provides a comprehensive blueprint for mastering this infrastructure, training professionals in the exact electrical and cooling architectures required to secure a career in this elite industry. The digital world needs physical protectors. Secure your certification and start engineering the facilities that keep the global network alive.